Think of a computer, but millions of times faster at solving certain problems. A machine that can break today's strongest encryption, simulate molecules with atomic-level accuracy, and solve problems classical computers couldn't finish even in the lifetime of the universe. Hello learners, welcome back to my Tech Talk channel SmartBot Sphere. In this video, we'll understand what quantum computers are, how they work, and why the world is racing to build them. Welcome to the world of quantum computing. Every device we use today, your phone, your laptop, even powerful servers, are classical computers. They use bits as the smallest unit of information. A bit can be either a 0 or a 1. Quantum computers, on the other hand, are built on the principles of quantum physics, the science of very small particles like electrons and photons. Instead of bits, they use quantum bits or qubits. What makes qubits special is that they don't behave like normal objects. They can operate in completely different ways because they follow quantum rules. These rules allow quantum computers to explore multiple possibilities at the same time, giving them the ability to solve certain problems exponentially faster than classical machines. So, what exactly is a qubit? Imagine a regular bit as a switch. It's either on or off. But a qubit is more like a dimmer. It can be on, off, or any combination of both simultaneously. This is called superposition. A helpful analogy is a spinning coin. When it's spinning, it's not purely heads or tails. It has the potential to be both until it lands. Similarly, a qubit in superposition holds multiple states at the same time. This ability gives quantum computers massive parallelism. Where a classical computer tries solutions one after another, a quantum computer examines many possibilities together. This is the foundation of their incredible power. Number 1 is the superposition. Superposition is what lets a qubit exist in multiple states at once. If you had two classical bits, they could represent only one combination at a time, 0, 0, 0, 1, 1, 0, or 1, 1. But with two qubits in superposition, a quantum computer can represent all four combinations simultaneously. With 20 qubits, it can represent over 1 million states at once. This exponential growth gives quantum machines unprecedented computational capacity. Entanglement is one of the most mysterious phenomena in quantum physics. When two qubits become entangled, they form a deep connection. Change the state of one qubit, and the other reacts instantly, no matter how far apart they are. Even Einstein struggled to explain this, calling it spooky action at a distance. In quantum computing, entanglement allows qubits to function as a unified system. They work together, coordinate instantly, and create patterns that classical computers cannot replicate. This is essential for creating meaningful results from quantum algorithms. Next concept comes is interference. Interference is what allows quantum computers to amplify correct answers and cancel out incorrect ones. Think of waves in water. When two peaks meet, they grow stronger. When a peak meets a dip, they cancel out. Quantum algorithms use this behavior to steer calculations toward the right solution. Superposition explores possibilities. Entanglement links the qubits, and interference filters out the noise, leaving behind answers with extremely high probability. Quantum computers are nothing like regular computers. They're extremely sensitive, and even tiny vibrations or temperature changes can break their quantum state, a problem called decoherence. To prevent this, quantum processors are kept in special environments. Many quantum systems operate inside dilution refrigerators. Machines that cool the processor to temperatures colder than outer space, often just a few millikelvin above absolute zero. Inside this ultra-cold environment sits the quantum chip. It doesn't look like a normal CPU. Instead, it's covered in patterns of superconducting loops, trapped ions, or photonic circuits depending on the technology used. Qubits are controlled using precise microwave pulses, lasers, or electromagnetic fields. These pulses manipulate the quantum states, putting qubits into superposition, entangling them, or performing measurements. Quantum algorithms like Shor's algorithm for factoring or Grover's algorithm for search take advantage of quantum mechanics to achieve speedups impossible for classical computers. Quantum computers may still be in development, but their potential applications are extraordinary. Number 1. Break encryption. Traditional encryption methods rely on mathematical problems that classical computers take too long to solve. Quantum algorithms could break these systems in minutes. This is why countries and organizations are already preparing quantum-safe cryptography. Number 2. Drug discovery. Quantum simulations can model molecules at atomic precision. This can revolutionize medicine by predicting how drugs behave before real-world testing. Number 3. Financial optimization. Quantum computers can analyze massive datasets and test thousands of scenarios simultaneously, helping banks and businesses make smarter decisions. Number 4. Artificial intelligence. Quantum machine learning could dramatically accelerate tasks like pattern recognition, model training, and optimization. Number 5. Climate modeling. Simulating weather patterns and chemical reactions at quantum level could improve our understanding of climate change and help design solutions. Quantum computers face significant challenges. Qubits are delicate and prone to errors. Environmental noise can destroy quantum states in microseconds. We need powerful error correction systems and more stable qubit technologies before we reach fully fault-tolerant quantum computing. Hardware is also expensive and difficult to maintain. Dilution refrigerators require enormous energy and complex engineering. We are still in the early stages, but software companies are making progress which is accelerating. The future of quantum computing is incredibly promising. Many experts believe we will soon achieve quantum advantage, the point where quantum computers outperform classical supercomputers for practical problems. We may see hybrid systems where classical AI works alongside quantum processors. This combination could unlock entirely new industries, smarter simulations, and more efficient technologies. Quantum computing is not just an upgrade, it's a revolution in how we think about information, logic, and processing. Quantum computing is still young, but its potential is limitless. As the technology matures, everything from medicine to security to AI will transform in ways we've only begun to imagine. I hope this video gave you good enough idea about quantum computers. If you enjoyed this, please make sure to like the video, subscribe, and tell me in the comments what topic you want next.